We are ready to go. So welcome to the second day of the first series in new topics meetings from the Mineralogical Society. We had 4 talks yesterday and we are looking forward to 4 more talks today. And just to give you a brief update, we have been asked to provide list of basic references for students to start reading into the topic if they would like. And we are currently compiling such a list, and it will be available online on the web page together with the videos, as far as I understand. Right, Kevin?
Yes, that's correct.
Cool. So we are ready to go, and we welcome our first speaker, Clare Warren from the Open University. And yeah, Claire, it's all yours.
Thank you very much. Thanks for the invite to give a talk today. So it's my role to talk about thermochronology, the stuff that I'm interested in, dating rocks, the theory, but also a bit about the reality. So thanks very much to the list of co-workers down the bottom of the screen there. But any mistakes in here are definitely my own, nothing to do with them. So one of the things that we like, or lots of things that we like to find out about as geologists, but it's the big picture story. It's these tectonic events, trying to figure out when rocks were buried, when continents collided, when bits of oceanic crust subducted beneath other bits, but also the metamorphic rocks and the igneous rocks that record those events and those processes. And in order to understand some of the mechanisms by which these crustal materials move around, we need to understand the timescales and the rates as well. So when did these events happen? How quickly did they happen? How long did they take? And in order to answer those questions, we have to go back to the rocks and try to figure out how the rocks actually recorded their history. So which bits did it record, and what do those records actually mean? So thermochronology is the sort of the science and the practical art, if you like, of trying to unravel thermal histories from minerals in rocks, and particularly using the chemical and the isotopic and the physical properties of rocks that change with respect to both temperature and time. So there are lots of isotopic systems we use to date rocks, which are traditionally used in a thermochronology sense. So meaning that the ages that they record are younger than the timing of crystallization of the mineral itself. So potassium, argon, uranium, thorium, helium are the common ones, fission tracks, but they're not really to do with diffusion, which we're talking about today, but also other mineral schemes, isotope schemes like uranium, lead, samarium, dimium, lutetium, hafnium. They can all be thermochronometers if the temperature is high enough and the time is long enough. So Thomas showed this, or Sumit showed this picture yesterday. We traditionally think about geochronological decay schemes in terms of the temperatures that they can, over the temperature ranges over which that they're useful for, or what they actually record. And this is quite a good starting point. We all get taught this at undergrad, but by the time we actually start looking at the details, we realise that this isn't actually particularly useful in detail. So what I'd like to sort of take home message really today is to be very, very careful about making assumptions about what ages mean from different minerals measured by different decay schemes. So argon dates of muscovite do not always mean cooling through X degrees, for example. You've got to be very, very careful with those interpretations. So in theory, we make the assumption that our daughter elements are lost from the mineral via a thermally activated volume diffusion. And as was mentioned yesterday, the idea is that when these daughter isotopes reach the edge of the grain, they mysteriously vanish into this beautiful, infinitely accommodating and vanishing reservoir, and they vanish from our thought and from our analytical techniques. And this isn't always the case. We also make the assumption there's no initial daughter product in the grain. So in common with common lead in the uranium lead decay scheme, we're talking about argon that may or may not be in the muscovite when it crystallizes, for example, or any helium that's floating around before the uranium that's in that crystal starts to decay. We also make the assumption that there's a uniform parent isotope distribution within the grain, and we know that quite often this is not the case either, especially when you start talking about zoned minerals. And then, as I've already said, this infinite grain boundary reservoir that makes all our daughter elements mysteriously vanish out of the grain that we're interested in, such that there's a perfectly open system. And that is definitely not the case in a lot of metamorphic rocks as well. So what we assume, or saying hope happens, is that your mineral crystallizes at a certain temperature, and the clock starts ticking, the isotope decay starts. And then as the mineral is cooled, slowly but surely some of the daughter isotope is lost, but not all of it. So the clock is either not recording or it's partially recording. And then at a certain temperature, sort of formally formulated by the Dodson closure temperature idea, the clock starts recording. But of course, this is a very, as we spoke about yesterday, the Dodson closure temperature idea is a lovely, very simplistic idea that doesn't apply in detail to real messy natural rocks. And now that we can start analysing some of these elements much more carefully than we could in the 1970s, and I realise that's 50 years ago already, that actually we need to start looking at this much more carefully now. So what we hope we get whenever we're dating a rock or mineral is a perfect single age population, that we can say it's this age at that point in time, this geological event happened, and we can all just like shake our hands, write our paper, and off we go, job done. So in argon, that would involve a nice flat plateau. In uranium lead or any other system, just a nice little population that gives us a nice tight average and a nice low MSWD, and we're all happy. But of course, we know that as we measure or we date rocks with more and more spatial, fine spatial precision, we end up getting more and more dispersion. So in argon, we might get these wonky step heats. There's no plateau here. Or in single grain fusion, or in uranium lead monazite or rutile data, we might get a big dispersion. And in these particular rocks, this is data from the Western Gneiss region in Norway, we've got about a 50 million year spread in age or date. And of course, that's meaningless when you're trying to link that, trying to date one particular event or one particular thing that's happening. But this dispersed data is really informative because it can tell us a bit more about the process which led to the mineral recording the time that it did, that the point at which the clock in that mineral started ticking. So there's lots of different processes that we currently think can affect the record of age or the isotope ratio that is finally resulting from our analysis. And that can include diffusion, and then diffusion, of course, is linked to thermal history, it's linked to mineral chemistry, it's linked to the grain size and shape, and again, the grain boundary openness. But there are other things as well which we need to take into account, especially in natural, messy, metamorphic rocks and some igneous rocks. So deformation, that can add or lose daughter isotope. Recrystallization can do as well. Fluids coming in or out can bring elements along for the ride. And so the important thing here is how can we differentiate between these different processes that are operating or have operated in our rock, and also understanding which is the most important for actually ending up with the isotope ratio, the age in the rock that we now measure. So there's a bunch of questions that you always need to ask of your samples and your data even before you start. So is the thermal history conducive to diffusion? Like if it's a fairly low temperature rock or it's cooled very, very quickly, has there been enough time and enough opportunity for diffusion to actually start affecting the daughter isotope that's sitting in our mineral? Are we ever likely to get a cooling age, or is a crystallization or contaminated age the only thing that's likely? We can model our system, what we think's happened to that rock in terms of pressure, temperature, time, space. What does that look like? What are we expecting to get from our perfect rock? And then we can have a look, do the data and do the models match? And that might be informative. It might tell us something about the reality of the pressure, temperature, time history that rock's experienced, or it might tell us that actually some other process has happened to affect the age recorded in that rock. And then, of course, which analytical methods will best answer your question? I mean, if you just want to know whether your rock is Precambrian or Miocene in age, it doesn't really matter what analytical technique you use, you're going to get roughly the right answer. But if you want to know whether that rock cooled between 600 degrees C and 400 degrees C 10 million years ago, or between 10 and 12 million years ago, then you're going to have to use a different analytical technique to actually gather those data. And then finally, are you actually dating diffusive loss in that mineral, if you're thinking about thermochronology, or are you dating something else? Are you dating the timing of deformation in that rock, or the time of a pulse of fluid flow, or something like that? So the first thing you need to do of any sample is actually develop your pressure temperature framework, and if possible, pepper that with other bits of timing information that you have from chronometers that absolutely record the timing of crystallization of different phases. So you need to look at your petrology very carefully. You need to look at your mineral chemistry very carefully. You might need to do some pressure temperature modeling, so either using a pseudo-section or isochemical phase diagram, or some of the more conventional pressure temperature sort of determinants. And the minerals that you're then dating, when do they appear in that framework, in that history? What pressure temperatures do they crystallize at? What pressure temperatures might they have changed their composition at? Where do other phases that might be competing or producing the daughter isotope that you're interested in measuring, where do they fit into the picture as well? Because all of these parts of the story will help you interpret the data that you're collecting. So once you've got your pressure temperature history, or at least what you know, the framework that you think that your rock's been sort of experiencing, then you can start to look to see whether diffusion is likely or possible. Or certainly, diffusion obviously is always happening, but the rates at which it happens may not be important even on geological timescales for the analytical techniques that you've got to measure. So here's an example for the retention of argon in muscovite. This particular plot is for 1 millimeter grains held at these conditions for 500,000 years. So anywhere that's red, so this is the temperature and pressure on the y-axis there, anywhere that's red is going to have at least 80% of all the argon in that grain retained after 500,000 years. So you then have to decide, and you convert that retention into sort of time, whether that's a time period that you can actually measure using the analytical techniques you've got and the time period you're interested in. And then in blue here, you're only retaining about 20 to 30% of argon. So you could, in theory, lose a lot of the argon, and then your mica might give you a cooling age. And obviously these kinds of diagrams will vary depending on the grain size, the mineral you're interested in, the isotope decay scheme you're interested in, and how long you're going to keep that grain at those pressure temperatures for. And obviously in a real metamorphic rock, you're also cooling. So these are sort of a maximum amount of argon that you can lose. You can also model the core to rim variation in age that you might expect for different cooling scenarios. So this is some calculations from the Oman high pressure rocks. The uranium-lead zircon suggests that the eclogites crystallized about 80 million years ago. And then you can sort of model different scenarios for different cooling rates as to what you might expect a 1 millimeter muscovite grain or phengite grain, what you might expect the ages to be if you cool at different rates. So if you cool very quickly, the difference in age between your muscovite and your zircon is going to be really small. Can you actually measure that with the analytical equipment you've got? But if it cooled very slowly, then maybe the age range would be big enough. And you can also then see the difference in the ages you would expect to find from the core to the rim as well. So you can sort of see these profiles developing. And if you've got the right analytical equipment, you might be able to look for those profiles and then match it up with these kinds of models and say, yes, my rock cooled at 25 degrees C per million years from 75 million years ago, or whatever. So you have to choose your analytical method. Obviously, the more material that you put into your mass spectrometer, the better the counting statistics are on both your parent and your daughter isotope. So you're going to get much better analytical precision. But you're also likely to get much more analytical mixing or geological mixing of your sample. So especially if your grains are zoned, or if you're by accident you've got a bit of contaminant sitting on your mineral or whatever, then you might end up with a very precise but geologically meaningless average. So whether you're throwing handfuls of grains at your mass spectrometer, or you're picking out individual grains, or you're looking sort of at much finer scale, you need to pick the method that's going to be the most useful for you. There has been a huge amount of development in situ work over the last 20 years or so, starting with uranium lead, but now increasingly moving on to the thermochronometers, the argon-argon, uranium, thorium, helium, things like that as well. You get much better spatial precision, so you can start looking for zoning in your minerals. But because you're measuring less material, you're going to have much worse counting statistics, so your numbers are going to be less precise. And obviously, as instrumentation improves, the precision gets better and better again. But you can separate out zones of different chemistry. So that's been one of the major advances, obviously, in dating things like zircon and monazite, is you actually see different growth zones, and you can actually date those different growth zones. So you can get a much better idea of the rates and timescales of the metamorphic process or the igneous process that you're trying to measure. And the other thing you can do now with the in situ work, we were talking a bit about this yesterday, is depth profiling. And once you start measuring either your element or your isotope ratio from the outside of the grain inwards, then you can start matching up to models of perfect diffusion. Do they match? Can you say that diffusion has been a dominating process in this particular mineral? So what we want to actually be able to start looking for is how much evidence do we see for diffusion being responsible for the dates that are recorded in thermochronometer minerals. And there's lots of different progress on this, and certainly in the high temperature rocks. So this, for example, is rutile in a quartz granulite from the Ivrea zone in the Alps. Then depth profiling has shown that you do get these really nice profiles. So there's much younger ages recorded right at the rim, and as you go into the grain, you get older and older ages. So there has been a diffusive loss profile, and you can model those profiles. And in this particular instance, they suggested rapid cooling from 600 degrees C, and then slower cooling later from 525 to 480 degrees C. Now, if you've worked a lot on the Ivrea zone, that might or might not make sense, but that appears to be what these rutiles have recorded. If there was just diffusion going on that was removing the lead from these grains. And that's making the assumption, again, that the grain boundary is completely open. And the moment the lead gets into that grain boundary, it just vanishes and never goes back into the rutile, doesn't go and sit in the quartz. And we know that that's very unlikely to be true, given what we heard yesterday. But again, it depends on what question you're asking. If that's good enough, then that's good enough. This is another example from a gem quality feldspar from Madagascar, and a big pegmatite. And you see these really nice profiles. So this is the large distance profile from rim in towards the core, and then in finer detail at the bottom here. But this particular experiment showed that the laboratory-derived diffusion rates for feldspar do seem to hold and make sense. They seem to be valid in nature over geological timescales. So that was a really nice sort of proof, if you like, because there have been lots of questions about whether the diffusion parameters for argon in feldspar that are laboratory derived actually represented what happened in nature. And in a perfect situation, perfect cooling scenario, they do. And this again was modelled with rapid initial cooling and then slower cooling later, and that seems to sort of fit other geological evidence. But sometimes you end up with a bit of a mixture, and you end up with complicated systems that are difficult to unravel. And this is where you need to use other chemical clues in exactly the same way that we do with sort of petrochronological techniques for zircon or for monazite, where you use, for example, rare earth elements to give you extra clues about what the uranium-lead systematics are telling you. Well, here in the argon-argon world, you can use the artificial radioactive production of 38 calcium to 38 argon when you irradiate your sample, and 37 chlorine to 37 argon, as trackers of calcium or chlorine bearing contaminants or mixtures in some of your minerals. So here, for example, there's a mixture of hornblende and K-feldspar. And if you're extremely careful at separating out your pure hornblende, it has an age of about 500 billion years. And if you separate out pure K-feldspar, it has a much younger age, sort of well below 50 million years. But any kind of mixture of the two, and you end up with this really wonky wonky step heating spectrum, where you can't disentangle the 500 million year age from the 20 million year age, or whatever that one was down there. But by looking at the chlorine to potassium and the calcium to potassium ratios, which are very different between the hornblende and the K-feldspar, you can start to unravel a mixing line. And so you measure your chlorine and your calcium and your potassium on the electron microprobe, and then you can actually start disentangling for each step what mixture there is between those two different minerals, different phases. And then you can actually extrapolate back to get the correct ages of each end member. So it's a little bit rough and ready, but it does work. And you can do this when you've got different mixtures of the same mineral as well. So here's an artificial example of two biotites, one which is about 146 million years old and one which is about 75 million years old. And then these sort of wonky step heats in the middle are 1:3, 1:1, and 3:1 ratios of those two end members. And if you just looked at that diagram, you would never be able to untangle the mixture. And if you think about sort of natural samples, you get these wonky step heating spectra all the time. And they're very difficult to disentangle what the wonkiness means, because there are so many different ways that you can make a plateau, a non-plateau. But again, by disentangling measuring the 38 calcium as 38 argon, and so when you're measuring all your argon isotopes, you can start disentangling this mixture and disentangle what the two end members are as well. So it is possible, but these all require mixing quite large volumes or measuring quite large volumes of your samples in order to get enough 38 argon and 37 argon to measure. It gets much more difficult when you are looking at very fine-grained micas. So here's one of these sort of mica mats, and you get these quite often when you deform, say, sandstones or something at fairly low temperatures. You get these mixtures, these mats of very tiny grains. And an SEM image can sort of show different compositions all mingled in together. And this circle is sort of the size of the laser spot that you might employ to actually measure the argon isotopes to disentangle the two. Now, again, if you step heated a lump of this, you'd sort of get a bit of a mess. Or you could laser lots of different spots on a mat like this and start to look at different isotope ratios. So here the chlorine to calcium, for example, and plot that against the ages you get for the different analyses. And over lots of different analyses, you can start seeing a sort of trend towards a younger component and an older component. And this particular example, the older component was detrital, and the younger component must be the sort of metamorphic new deformation age. And so if you try and pick your spots with as much of that younger component, the new muscovite, as you can start trending to younger and younger age, and you can start figuring out when that deformation or microcrystallization might have happened. So you can actually use both the in situ and the larger, coarser techniques to try to unravel as much information as you can. So just a final sort of messier example. This is the Western Gneiss region in Norway, where you've got 700 degrees C and about 15 kilobars. So 700 degrees C for white mica argon-argon systematics should be absolutely plenty of high enough temperature for the argon to be flooding out and lost to the world. Now, petrologically, this white mica is being replaced by a biotite and and plagioclase of symplectite around the edge. And so the idea was to look at the ages recorded by the different phases in these different samples. So going from an eclogite through to an amphibolite, and then some of the rocks in the middle sort of preserve this transitional assemblage. Now, in a perfect scenario with an open system at those kinds of temperatures, each of these minerals should be recording cooling ages. And so you should get a really nice sort of trend through time. Should be able to match the ages with the sort of closure temperatures of these minerals and get a nice cooling history out. In terms of the pressure temperature evolution, well, fengite's stable at high pressures. And as you decrease the pressure at high temperatures, biotite comes in, and then plagioclase comes in. Eventually you lose fengite. And we also have the titanite in, so rutile titanite line at lower pressures and temperatures. And this is important because titanite can be dated with uranium lead, so it gives us another sort of time point on part of this pressure temperature history. So the rock is clearly out of equilibrium because we're still recording bits of these reactions. But in theory, our argon-argon system shouldn't matter about the record. It should just be the temperature. But what we actually see is a bit of a mess. So it's a bit of a messy diagram, but this is age or date, if you like, from 350 up to 510 million years. These were eclogite facies rocks at about 400 million years ago, as shown by zircon uranium lead, which is fairly robust in terms of thermochronology. The titanites yield ages that are slightly younger than the zircon uranium lead age, and the red spots there, the average. But then look at the fengite data, okay? So it's slightly younger than the zircon, all the way through the same age as the zircon, all the way up to nearly 500 million years old. Now, there's no way that a subduction exhumation cycle is going to take 100 million years in this particular example. So these aren't ever going to be crystallization ages. So this is sort of a bit of these are all eclogite facies fengites. So this is clearly contamination. And then the biotites that are replacing the fengites, well, the symplectitic biotites, you had a sort of little cluster of younger ages here, but again, they overlap with the titanite. And remember that titanite comes in later on the pressure temperature path. And then the coarser biotites that grow from the symplectite later yield this spread of older ages. And then the plagioclase, which sort of grows at the same time as the biotite, yields all sorts of random number. It's like a random number generator, but they're all pretty old. So this is just a case of argon recycling. You've got a closed system where most of the potassium sitting in the fengite initially, and then over time the fengite breaks down and then you start moving your potassium out into the biotite and into plagioclase. But the argon's not disappearing. There is no magic grain boundary open network for the argon to flood out and disappear. So the fengite's yielding these heterogeneous ages that they're contaminated with excess argon. The argon during the prograde metamorphic cycle is also not being able to disappear. The biotite takes in some of the argon released as the fengite breaks down, so it has actually got a solubility, and you've got this sort of extra argon that's inheriting. So some of those ages are contamination related, maybe some cooling ages, but it's difficult to disentangle. And the plagioclase is clearly all contaminated. So whenever we date a rock, we really want to link the ages that we get from that rock to the stage of tectonic process or metamorphism or sort of igneous generation that we're actually interested in. So we need to start off really clearly with what actually is our research question. What are we trying to find out? Because if you're just trying to find out the age of the mica, well, fine, you just date your mica. But linking that age, that date that you get to actually some geological process is where the fun begins. The petrology is always really important. It doesn't matter how old-fashioned looking down a microscope may feel. You still need to know how many phases there are in the rock, especially with argon-argon. What are the potassium-bearing phases? Where's the argon going to partition to and from? What are the chemistry of our phases? What's the pressure temperature history of the rock? What's happened before that mineral crystallized that we're interested in? What happened to that mineral after it crystallized? The analytical methods we choose are really important. The The models are really important for insight, but also the petrochronological information is clearly important. So which other elements can we pull in that might act as fingerprints for different processes? So just in summary there then, thermochronology or sort of water fluid deformation hygrochronology, as Igor Villa has called it. The age discordances here are caused by a mixture of phases that grow over different times, and they're different chemistry. So we can unravel some of these histories. Volume diffusion is orders of magnitude slower than dissolution and precipitation. So unless you're in a really, really perfect system, it's very difficult to think that it's actually a thermochronometer age. And fluids obviously are nearly always present, certainly in metamorphic rocks, messing with the system. So the take-home messages really are that it's very difficult to resolve age populations in rocks without using some of these other tools. Multiple processes affect the dates that you get, and in order to turn those dates into ages, you need all this extra information. But dispersion in age is informative because it tells you that it's not just one process that has affected this rock, it's lots of things, and you need to disentangle them. The higher spatial resolution techniques do provide more detail, but you need to use them with care. And certainly when you're modeling or thinking about the assumptions that you're making about this rock before you start analyzing it, don't forget that garbage in equals garbage out. So just be very careful. And then finally, I guess, but these will be made available to everybody later, but there's just a list there of background reading, some good review papers on states of play and where we are with that. But more than happy to answer any questions. And thank you very much.
Thanks a lot, Claire. And it's always amazing to see that even for the argon or the noble gases, the assumption for infinite fast transport isn't actually true.
Yeah, you still need that infinite grain boundary reservoir. And many times it holds in general, but when you start looking in detail, it just all falls apart. So, yeah.
Yeah, so we have 10 minutes for questions, and I'll look into the chat. Are there any questions from the audience? Type it into the chat box or unmute yourself. Make yourself heard.
It's a bit of a whistle-stop tour through thermochronology. And I'm sorry if, for many of you, thermochronometry is as perfect as geochronometry, but it's not anymore. It's never that easy. It gets complicated and messy.
Okay, can I start the ball rolling?
Yep.
I'm too slow at typing into the chat, so I'm just going to have to ask you. We heard yesterday about how the presence of water in grain boundaries totally transforms diffusion rates, and yet with some of the examples you're showing, it's obvious that there's little bits of water around some of the time, but during cooling, equilibrium water fugacities go down to very, very, very small values. And so it's a transient phase that is only there briefly. But given that that is really screwing up the transport properties when it's there, does this mean that the problem is so awful that you shouldn't try and tackle it? Or does it mean that you can just assume that because it's there for a little bit occasionally, then actually it just takes over and everything comes out in the wash? What do you think?
I think what we're not very good at determining yet is when fluids were likely to be present in the rock. So at what pressures and temperatures, what other reactions were going on elsewhere that may be producing fluids that then transiently come through the rock at the time. So it's a mixture of when your minerals are closing to diffusion or when they're releasing stuff out into the grain boundary network, when there's a transport medium there to help bring material out. But out of your little sample that you're looking at is into the next one that somebody else may be looking at. So you're never sure where the material is coming in or out. So I guess overall, I'd say it's a solvable problem, but we haven't got there yet. And we need to be asking different questions of our rocks and putting more brain power behind it to try and unpick. In many cases, it probably doesn't matter that much. But again, it depends what question you're trying to find out. If you want to know when that rock cooled through 400 degrees C, it's a very different question to what is the age that my mica is giving me. The two aren't necessarily linked, is, I guess, the take-home message.
We had another question from Thomas.
Thanks. Hi, Claire.
Hiya.
About the Norwegian example and the white mica with this large spread in ages. I wonder if you do have similar type of information that from like Igor Villa, that you know that the oldest, for example, has oldest mica has certain calcium, or what was the other, chlorine component. Is there anything? Because I just tell you why. I mean, this would be
yeah. So the white micas are particularly difficult because they tend to not have very much calcium in them. Certainly in the high pressure rocks, and they certainly don't seem to have much chlorine in them as well. So the problem then comes is we are then limited to what we can measure analytically. I didn't go back to looking at the biotites and the plagioclases to try and unravel the calcium and the calcium, chlorine, potassium, but certainly in the white micas, it was just a sort of detection limit, so it's very, very difficult to do. So I guess what you'd probably need to do then in that case is go back to those rocks, pick out the white micas and do either single grain fusion or even step heating experiments, so that you've got that whole range of the bulk information to the finer scale information, and then try and pull it out that way. But we didn't do it. Those experiments predated some of the information in the Villa papers.
Just doesn't, are the micas clear and clean? That's, I mean, they look quite, I mean, there looks a lot of reaction going on. So this is,
yeah, certainly the cores of the fengites were quite clean. When you start to get to the symplectites around it, they were much messier, and it was difficult to get clean shots at them. So certainly in the symplectites, need to go back to the data, but you probably could pull something out. But even then, you can get maybe a mixing line between two numbers, whether those two numbers are actually cooling ages of either phase. You know, I mean, it's different when you're trying to date hornblende in an igneous rock, for example. You're expecting it just to have cooled in one go. Metamorphic rocks that's reacting and cooling in different stages are also complicated. So there's lots to be found out, but be careful of the questions you're asking.
Okay, Schumit has a question and asks you to elaborate a little bit more on what you think may have been going on with the fengites in the Western Gneiss complex. So what's your take on the age of the peak metamorphism then?
So I think that the eclogites formed around 410 to 400 million years ago. That seems to be what the zircon data are telling us. And in many of those rocks, the zircon data linked with other rare earth element data seem to suggest that those zircons are growing at high pressures. What we haven't figured out with the Western Gneiss region, which is a slightly complicated ultra high pressure region, is how long those rocks were sat at high pressures for, how quickly they subducted, and then how quickly they exhumed. So it's partly the exhumation story that we were trying to pull out. But what was clear from that data set was that none of those mica ages is yielding the ages of cooling through anything. Maybe the youngest date of each of those sets might be providing some information about that, but mostly what it's showing us is that the system is not open enough to get rid of all the argon that's being produced. The felsic rocks around the mafic rocks provided a clearer story, but less interesting for that particular example, so I gave the complicated one.
So what I was wondering, Claire, is over 500 a real geological age at all, or is it just some artifact?
Well, the rocks originally were Grenville age sort of crust. So there are the potassium in those rocks, if you like, is 1 billion years old. So there's plenty of time and opportunity for lots of argon to have built up in the system. And in those mafic rocks particularly, if that system stayed fairly dry and closed, even during subduction, a lot of that argon couldn't escape. So you've got 1 billion years worth of argon. Some of it can't escape, so that can easily sort of give you a 500 million year contamination age. But I don't think that sort of 500 million years is anything geologically reasonable.
Okay, thanks.
I think it's just a mix.
Okay, we have a little bit more time. I do see that. Yeah, no. So Bob,
Bruce is waving his hand again.
Okay,
just to follow up on that last point, Claire, surely it's unlikely that a white mica lattice was present in those rocks before the exodyne event.
But the potassium, there would have been potassium.
Yeah.
So there's potassium there in some form or another, probably in plagioclase, whatever. And then the white mica grew during metamorphism, but then probably maybe 450 million years ago, maybe that started subducting and making mica. But those micas themselves have got the high pressure signature in them. So they're sort of the high pressure bit of the story, but they're still likely to be retaining some of the argon produced much earlier. So the solubility is not zero. You know, we make this assumption with argon that there's no common lead equivalent, that we're not inheriting any argon to start with. But I think those kind of examples clearly show that you can, and you have to be careful.
Wonderful, and I see that participants found out the way to raise their hands. So I see that Bob raised his hand. Bob.
Yes, I did. Two comments. I started writing one in the chat and hit return by mistake. I think we should start from the assumption that the infinite reservoir does not apply unless we can make a specific case that it did.
Yep. I think so. I think it's causing a lot of problems because it's become one of these assumptions that's become such a sort of foundational pillar, especially when you're applying the sort of Dodson formulation closure temperature idea. That's become our sort of baseline assumption, and from then we're moving on from that. But actually that foundation's got no legs anymore. We should just remove it completely. Exactly. I agree. And the same with the idea of closure temperature. Just let's not think about it that way.
With Bruce's comment about the transient nature of fluids, it is not only transient, but it's also going to be spatially very variable, localized.
Yeah.
And most of the time, I would guess that fluid axis is related to deformation.
Yep.
And then you're going to see things on a very small scale. And the sort of thing that we saw with rubidium strontium on Syros, where we see grains less than a millimeter apart, giving quite distinct ages.
Yep. Yeah, and that's fascinating. You know, why is that one mineral recording this age and the one next door recording something different, when they probably either they crystallize at different times, or or they might have crystallized at the same time. But that whole pulling together, that whole story, I think is really neat. It tells you a lot about what the rock's history is.
Yeah, but makes it very hard to get tectonic scale.
Makes it hugely difficult to get tectonic scales.
Okay, so we have to move on in time. That was a great discussion. If you have more questions, we will have a final round of discussion at the end of the day, as we had yesterday.